Hello, I am Shunhao Oh from the Georgia Institute of Technology, and I'm here to talk about local stochastic algorithms for alignment in self-organizing particle systems. This is a joint work with Hridesh Kedia and Dana Randall. So in nature, there are many examples of macroscopic behaviors that arise from only local interactions. So some examples here are the flocking of birds and the synchronization of fireflies. So what is this alignment problem that we are studying? So we have this large body of particles, or tiny robots, that can communicate only locally. So each of these particles can only see its local neighborhood, or some neighborhood of constant size. And each of these particles has a randomly assigned orientation. So is it possible for most of these particles to somehow agree on one common orientation to align to? So if these particles are stationary, this is very similar to some kind of Potts model. So in the ferromagnetic Potts model, each configuration is an assignment of colors from 1 to Q to vertices of the lattice. And we have this stationary distribution defined over here, where the probability of a configuration sigma is proportional to lambda to the h minus h sigma, where h is the number of heterogeneous edges in the configuration. In other words, edges between particles of differing orientations are less favored in this model. And we know that in the Potts model on the lattice, at low enough temperatures, which means high enough lambda, in the stationary distribution with high probability, almost all of these particles will be of the majority of some majority orientation. But what happens if we allow these vertices, these particles, to move around in space? So an example of application is in particle locomotion or flocking, where each robot in the swarm has the ability to locomote independently, but with no global sense of direction. A collection of these robots will only move in arbitrary directions, so it causes some kind of disordered system instead of a collective flocking behavior. So there are some related problems. There's this problem called dilute spin systems, which is a similar model to ours, but in their model, the number of particles can vary because they don't see the particles as particles. And there are a number of works in control theory about flocking. This paper over here gives a good summary of some of these results. And our paper is very closely related to the following two papers, which is compression and separation on the APPROX model. Most of the proofs used in this paper are based on the ideas from these two papers. Problem formulation. So in our model, we have a set of particles that occupy distinct sites on the lattice, but they can move around. We also assume that this lattice has a toroidal topology, as in when a particle moves off the edge of one side of the lattice, it comes back in on the other side. We also assume that these particles are anonymous, they have no IDs, and they have only local interactions. So a particle can only see its local neighborhood. We also want these particles to have limited computational capability where possible, and at most constant memory. So in addition, we give these particles one of Q discrete orientations. Normally we would label them 1 to Q instead of drawing arrows like before. So in this case, we set Q to 6. We do this because it is nice to use 6, as there are 6 different directions you can move in on the lattice. So these particles can switch their orientations at any time. So we consider two different models for particle movement: connected SOPs and general SOPs. So SOPs means self-organizing particle systems. So for connected SOPs, we require our particles to always remain connected and hole free. So this is an example of connected set of particles that is not hole free, because this is a hole over here. And we can do this using only local moves as given in this paper over here, the compression paper. On the other hand, for the general SOPs model, we allow the particles to move around freely. So any move by a particle to an unoccupied site is a valid move. So we can actually separate, we can disconnect, and we can create holes. These are all fine in the general SOPs model. Approach. So how do we get our particles to align? So in this diagram over here, you can see that we drew lines between the particles of differing orientations. These lines are what we call contours. So what we will show in our proof is that these long contours will not exist with high probability. And if we can show that, this means that one of the orientations is going to dominate in the configuration. Short contours like this are not going to matter much, so we are going to leave them alone. But one important requirement before we can show that one orientation dominates is for the perimeter of the configuration, which is the length of the walk around the configuration itself, to be low. Because if the configuration is high, if the perimeter is high, we may get situations like this, where there are only short contours, but not one orientation will dominate. So the first thing we want to do is to show that our particles will cluster into a low perimeter region. So what do we want to show in the end? For connected SOPs, we show compression and alignment. So compression means having the particles form a low perimeter configuration, and alignment means having most of the particles be of the same orientation. On the other hand, for general SOPs, where we no longer have the condition of being simply connected, we show aggregation and alignment. So alignment is the same as before, but aggregation means having a low perimeter region where most of the particles are. So how do we get our particles to want to compress and align? So what we do is we define these local weights of particles. So a local weight of a particle basically defines the particle's preferences for local neighborhoods. So in this case, the particles want to have more neighbors, and they want to have more neighbors of the same orientation. We do it like this, where the weight of a particle is defined as lambda to the x times gamma to the y, where lambda and gamma are parameters larger than 1. And x is the number of adjacent sites, a number of field sites adjacent to you, to the particle. And y is a number of neighbors with the same orientation. So here are a couple of examples. You can pause the slide if you want to check with them. So with these local weights, we can define the weight of a configuration itself. So the weight of a configuration is just the product of all of the local vertex weights, particle weights. And what we want in the end is for the stationary distribution over the configurations to be proportional to the weights of the configurations. And we achieve this stationary distribution by following the Metropolis-Hastings algorithm. So on each iteration, a particle makes either a movement step or a change in orientation with some acceptance probability according to the Metropolis-Hastings algorithm that looks like this. And what's important is that this ratio over here can be computed by the particle using only local information. And this is because this ratio can be expressed in terms of just the local weights of the particles before and after the change. For our proofs, because these configuration weights are going to be proportional to the probabilities of the configuration, we will express the configuration weights in this form. This is equivalent to the product of local weights earlier, where P sigma is the perimeter of the configuration. So the perimeter being the length of this walk around the configuration, ignoring orientations. And H sigma is the number of heterogeneous edges between particles of differing orientations of the configuration. So in other words, we are favoring particles of low perimeter and few heterogeneous edges. Results. So as mentioned before, our goal for connected SOPs is compression and alignment, and our goal for general SOPs is aggregation and alignment. So a couple of quick definitions. For alpha greater than 1 and delta between 0 and 1, we say a configuration is alpha compressed if the perimeter of the configuration is at most alpha times the minimum possible perimeter of n particles. So the perimeter is the length of the walk around the set of particles, ignoring the orientations of the particles. On the other hand, we say that the configuration is delta aligned if there is some orientation such that at least 1 minus delta times n of the particles are of this orientation. So it's basically saying that most of the particles are of this orientation. And what we will show for connected SOPs is that when lambda and gamma are high, we get a configuration that is alpha compressed and delta aligned. On the other hand, if lambda and gamma are low, though still greater than 1, our configuration will not be alpha compressed and will not be delta aligned. On the other hand, for general SOPs, we have the same alpha and delta as before, but our definition for aggregation is slightly more complicated. So we say that the configuration is alpha delta aggregated if there exists a low perimeter region R. So low perimeter meaning that the length of this boundary is at most alpha times the minimum possible boundary length, such that within R, all but at most a delta fraction of the sites are filled by particles, and outside of R, all but at most a delta fraction of the sites are empty. So we show on the general SOPs model, which notably uses only one parameter. We will explain why it uses one parameter later. But when this parameter lambda is high, we get a configuration which is alpha delta aggregated and delta aligned. If lambda is low, we get a configuration which is not alpha delta aggregated and not delta aligned. Techniques. So most of the techniques used in this paper are based on those used in the compression and separation papers which I mentioned earlier. So I won't have that much time, so I will try to be brief with the techniques. So for compression and alignment in the connected SOPs model, the basic approach is to first show that we have a low perimeter configuration. We use the cluster expansion for this. Then after we show that there is a low perimeter configuration, we show alignment by using the bridging technique and the Powell's argument to show that that long contours do not exist with high probability. And when there are no long contours, we can show using some geometric arguments that most of the particles will belong to the same orientation. So from the compression paper, we know that in the absence of orientations, which is the same as saying gamma is equal to 1 in our weight of in the definition of the configuration's weight, we will have with high probability a configuration which has a perimeter at most alpha times the minimum perimeter. So that's what we call alpha compressed. But what happens if we have orientations? So when we have orientations, this single boundary P does not refer to a single configuration, but a collection of configurations. And so we need to consider the partition function of the entire collection of different orientations corresponding to this specific boundary P. And to estimate this partition function, we make use of what you call the cluster expansion. So to use the cluster expansion, we first need to express this collection of configurations as a polymer model. So in the polymer model, every pairwise compatible set of polymers will be a configuration. I won't go into detail here, but that's the basic idea. So to do this, we need to change our representation of the orientations to something that is based on the differences between the orientations. So this allows us to represent each configuration as a collection of polymers. So if once we do that, we can come up with this estimate over here at the bottom that says that the size of the partition function is between an exponent to a constant times n, the size of the volume of the region, plus with an error bound of a constant times the perimeter of the region. So because the error bound of this is bounded by the perimeter, it is dwarfed by the gain in weight by the perimeter difference when we switch from a high perimeter to a low perimeter configuration. So we're saying that this does not significantly impact the proof of the original proof of compression if our lambda is sufficiently large, because this constant over here depends only on gamma. So after showing that we have a low perimeter configuration, the next step is to show that the long contours will not exist with high probability. And we know that if we can remove the long contours, that allows us to show that a single orientation will dominate. And the way we do this is using this bridging technique. So what the bridging technique does is try to bridge the long contours by connecting them to the boundary of the configuration. And we do that with a small number of bridges if possible. Using a small amount of bridges allows us to limit the number of possible bridging systems, which will limit the fan-in for the Bowles arguments later on. So what we notice is that the bridging argument is going to miss the small defects, and that is okay, because in the stationary distribution, there will always be a constant fraction of defects that are going to occur with high probability. So the Bowles argument looks something like this. When we remove these bridges, these contours, this gives us a gain in weight of something like gamma to the L, where L is the total length of the removed contours. And we can also show that the number of bridge systems is at most C to the L, which limits our fan-in to C to the L when we do this mapping. And so because gamma to the L is going to be greater than C to the L for large enough gamma, we can show that the kinds of configurations that we will see with high probability are going to look like this rather than like this. And this means a single orientation should dominate. So what happens in the general SOPS model? So recall that in the general SOPS model, our particles are no longer required to remain simply connected, which means we allow disconnections and we allow holes. So there are some problems that can occur when we try to apply the previous arguments to the general SOPS model. And the main one is that even if the configuration has managed to cluster into a small low perimeter region, this set of particles is unfortunately still going to have a high perimeter due to the defects that are going to occur. So unfortunately, these defects, there's always going to be at least a constant fraction of defects in the configuration with high probability. So what can go wrong is that in the partition function computed by the cluster expansion previously, there is an error bound over here that depends on the parameter of this configuration. And unfortunately, this parameter is going to include these holes. And so the parameter is going to be potentially linear on the number of particles in expectation. And that's too high because for the compression argument to follow through, we need this error to be at most root n, where n is the number of particles in the configuration. So for the general SOPs model, we use a slightly different weight function for configuration, where we use only a single parameter, lambda, and it's lambda to the minus a minus h. So h is the number of heterogeneous edges of sigma, and alpha is the number of edges between occupied and unoccupied sites on the lattice. So basically, if we look at it in terms of local weights, it is the local weight of a particle is lambda to the x plus y, where x is the number of particles adjacent to you, and y is the number of neighbors with the same orientation. Yeah, examples are over here. So basically, the particle prefers having more neighbors and more neighbors of the same orientation. Similar to before, but we use only a single parameter. So what is our approach for general SOPs then? So this time, we treat the unfilled sides of the lattice as another orientation. So we have Q plus 1 orientations. Take note that this strategy doesn't actually work in the connected SOPs case because it works slightly differently from another orientation if the set of particles is required to be connected, simply connected. Yeah. So if we treat this as another orientation, we can apply the bridging argument directly to the Q plus 1 orientations on the lattice. But there's one extra thing we need to do, because after we apply the bridging argument, that actually removes a lot of particles, and the number of particles may not sum up to n after that. So we need to apply one additional argument, which is what we call banking, which restores the number of particles back to n. And similar to before, we show that in the absence of long contours, aggregation and alignment will occur with high probability. So this is an illustration of the technique. We apply bridging. So as you can see, bridging removes most of these particles, and the number of particles is no longer the same as before. So we need to apply banking, which creates a minimal perimeter region, which may be, like you see, we have a gain in weight when we remove these contours. But when we build this thing, we lose weight, which is bad for us. But because we built a minimal perimeter configuration, this loss in weight will be less than the gain in weight. And that allows us to show that this is still favorable for us. So a couple of open questions, or rather things that we have yet to solve. So the first is convergence times. So because our model is similar to a POTS model at low temperatures, our mixing times may be slow. But it does not imply that it takes a long time. It still takes a long time to reach a compressed, aggregated, or aligned configuration, because this may still be fast despite slow mixing times. And also, the general SOPs model may be faster than the connected SOPs model because it has less rules to follow in its movements. So that's a possibility that we are exploring as well. And the other thing that's open is maybe a 2-parameter model for the general SOPs. So currently we use the 1-parameter model because it gives us a more straightforward proof that actually works out, because the other proof does not work. But this proof that we use does not easily generalize, and we would like something that's more flexible to differing, like to slight changes in weight. That's all for the talk. Thank you very much.